Hi everyone, my name is Pavel Blinov. I am a data scientist at Sber AI Lab and I'll present our workshop paper Semantic triples verbalization with generative pre-training model. This paper summarizes our participation experience at this year's Web NLG Challenge. We primarily were interested in the RDF-to-text generation task only for the Russian language because it kind of relates to one of our work project. Let me briefly remind of the task formalization. So the challenge task was to build a system that for a given set of input RDF triples is able to produce the verbal equivalent in natural language. Here you can see a small example. We are given the set of 3 triples about the manner, when and by whom it was built, and below one variant of its possible verbalization. The challenge organizers provided us with trained data along with the data split. This slide presents the count statistics about each dataset part. As well, you can note that the triples and verbalization pairs were collected from 9 DBpedia categories. Additionally, we tried to augment the trained part with similar data. We translated about 200,000 entries from Chinese to Russian, and our hope was that the performance can be improved with a sample of this data size. But it has an ambiguous result, and at the end we stick with only the provided dataset. In the trend of modern tendencies, we approached the problem with transformer-based neural architecture models. As our problem at hand requires the text generation, we selected the GPT-2 architecture as it was specifically designed for the language modeling task. Given the start of a sentence, such a model should produce probability distribution over all vocabulary tokens, and by iteratively sampling from this distribution we can continue our sentence. But here our task is slightly different from ordinary language modeling, and we want to force the model to repeat the meaning from an input RDF set. For this purpose we add an additional classification head which is trained exactly for this task, distinguish between fake or plausible endings. This head operates on the same text representation as the language one. And the final loss function for fine-tuning is the sum of 2 cross-entropy components. The one advantage of transformer models is that they require minimum text preprocessing. We've done only lowercase on an input text. Also, we try to add special learnable tokens for separation between predicate part or triples itself, but haven't seen an improvement and stayed with original vertical separation and new line symbols. The sampling from such trained language model is another part of a story. Here I listed several algorithms and strategies. The first two of them are deterministic but have several drawbacks. The other sampling algorithms implies a bit of randomness. That means that each drawing procedure can produce a slightly different verbalization candidate. By combining four last methods, we set up the generation pipeline with four control parameters. Here they are highlighted in bold. At the end of each generation procedure, we've run some post-processing on a verbalization candidate like parenthesis or brackets concatenation or float delimiter unification. And further, we run the number of experiments to find out how our parameters influence the metrics and find their best values. The plot here presents the blue metric dependency for the range of parameter values. As you can see from A part of this graph, the most influential parameter is the number of generated verbalization candidates, and you need to produce at least 11 different verbalization variants to reach some kind of performance plateau. For the other parameters, the range of acceptable values is wide enough and dependency isn't obvious. Here you can see different performance metrics of our system on def and test parts of the data. It's worth to note the large gap between the def and test. We suppose this is because of the way test data were selected, and already seen entries and categories were presented in the test data. At the rightmost column is our attempt to estimate the theoretical range of evaluation metrics for the def set. The procedure was the following. As the most entries in the train contains several verbalizations, we selected one at random and computed the metrics against the rest as the references. By this process repetition, we can estimate metric means and their standard deviation values. So we can summarize our experience with the following conclusions. Also, it's worth to note that it was always challenging to assess the system producing results in natural language. The organizers performed the human evaluation according to 5 criteria. Our system was able to overcome the baseline for all criteria except the data coverage. Therefore, our proposed approach is viable, but should be further improved in the direction of best candidate selection and fullness of preserved information. For this, we'll consider to build a separate ranking model. And that's it. At the end, I want to thank the challenge and workshop organizers for their effort, and thanks for your attention.